Okay, let's do the second problem of the 1988 mechanics free response test. And we've got this complicated little structure here. Take a look at the picture. I've got two springs. I've got this mass that's moving down this tube right here. It's a 5 kilogram object, slides with a speed of v0 in a hollow frictionless pipe. The end of the pipe contains two springs, one nested in the other. As shown, the object makes contact with the inner spring at point A, moves 0.1 meters to make contact with the outer spring at point B, and then moves on and moves an additional 0.05 meters before coming to rest at part C. The graph shows the magnitude of the force exerted on the object by the springs as a function of the object's distance from point A. So here's the force versus distance graph. We're going to use that quite a bit here. And let's get started on part A. Okay, so the first thing it says is, for part A, is calculate the spring constant for the inner spring. So let me zoom in here. So we want to know what the spring constant is. Now here's the big idea. If you have a spring and you have a graph of the force as a function of the displacement of the spring here, that slope is the spring constant. So for part A, I would write, okay, K, the spring constant K, is equal to the slope of this. That's delta F over delta X. Now, if you don't know that, that's a big idea that you need to know. What is the spring constant in a graph? Okay, so then you plug in your values. Well, what is delta F? Well, it starts at 0, goes up to 20 newtons. So that's 20 newtons. And then the delta X, well, it starts at 0 meters and ends at 0.1. So 0.10 meters. And that gives you a spring constant of 200 newtons per meter. Easy does it. Okay, that's part A. Okay, now part B. Calculate the decrease in kinetic energy of the object as it moves from point A to point B. Okay, now there's several ways you can look at this, but I like to do this. First of all, I'm going to use the work energy theorem here. The work done by the net force will be equal to the change in kinetic energy. Now, here's one thing to see. This force, the force that the springs are actually applying to this moving mass, the force is to the left. Does that make sense to you all? The spring is going to push this mass that way, to the left. Oh, I'm sorry, I'm off screen here on the picture. When this mass hits that spring, the spring is going to slow it down. It's going to do negative work. Okay? So the work done is negative. Now, the other thing you have to realize is that what work is the spring doing? Well, where is work in this graph? It's right in there. It's the area underneath the graph. So I'm going to say the work done is the area of that triangle, which is 1/2 the base, which is 0.1 meters, times the height, which is 20 newtons. And what is that? That's going to be 1 joule. Now, it's really taking away 1 joule of energy. It really is negative 1 joules of work. So I'll go ahead and add that negative in there, even though it's not in that area. And then I'm going to say that's going to be equal to delta K. Well, that's what it asks for. Calculate the decrease in the kinetic energy of the object. So whether you want to say delta K is negative 1 joule, or you can say we decreased the kinetic energy by 1 joule. You can say it either way. Now for part C, okay, let me zoom up. For part C, it says, calculate the additional decrease in kinetic energy of the object as it moves from point B, which is here, from point B to C. Okay, from point B to point C. Really what all you need is the additional decrease of kinetic energy is the area of this guy right here. And that's what you had to recognize. So how are we going to do that? Well, what is the area of that? You could do, I like trapezoids. Are trapezoids okay with you? Can you figure out the area of a trapezoid? If you can't, you can treat it as a rectangle and a triangle. Either way, you'll get the same answer. Oh, let's just do triangle and rectangle and triangle. What's the area of this? Well, it's the base, which is 0.05, times the height, which is 20 newtons. And then the triangle is 1/2 the base. And what's the height from 20 to 60 is 40 newtons. And this is the work done by the spring. And this turns out to be equal to 1 joule plus, and this is 1 joule. So the answer is 2 joules. Or we decrease the kinetic energy by 2 joules. Calculate the additional decrease in kinetic energy. So you can say delta K equals -2 joules. Or I think it's okay to just leave it as 2 joules of decreasing kinetic energy. Okay? Are we good? Okay, now part D. Calculate the initial speed of the object. Well, we know that the work done by the net force, all the net work done, the work done on this object will be equal to its change in kinetic energy. But how much total work was done on the object to make it stop? From here to here, we had, well, there's 2 joules here and 1 joule here. There's 3 joules of energy. So we lost 3 joules of kinetic energy. That's K final minus K initial. Okay? Well, what is K final? What's the final kinetic energy? It's 0, right? Because it says the object comes to a stop when you get to point C. So it has no kinetic energy at the end. So K final is 0. So -3 joules equals -K initial, so the negative goes away. And so we have 1/2 mV0 squared is equal to 3 joules. And then we solve for V0. V0 is equal to the square root of 2 times 3 joules divided by the mass. The mass was 5 kilograms. And when you do that, you get a velocity of 1.10 meters per second. And that's the answer to part D. Okay. Now you're going to need to look at the solution guide to figure out how many points you earned based on what you showed. And then, now E is the trickiest one. And so E, you want to know, calculate the spring constant of the outer spring. So, I mean, think about it. Here's what we've got. We've got the spring constant of this guy that we know, but then we need to figure out what the spring constant is of that. Well, let's think of this in terms of energy. There's no friction in this problem. We're not creating any internal energy or we're not heating the environment or anything. All that energy had to go somewhere, and it's really conservation of mechanical energy. The initial mechanical energy is going to be equal to the final mechanical energy. Now, what was the initial mechanical energy? Well, it was all our initial kinetic energy, which we know what it was. It was 3 joules. That's all that kinetic energy, which is, like I said, 3 joules. Now, where did it all go? Well, it went into the inner spring and went into the outer spring. Now, what is the energy stored in a spring? Well, it's 1/2 kx squared. And that is on your equation list. But they give you 1/2 kx squared, x squared. And we'll put this for the inner spring, and we know this, plus 1/2 k for the outer spring, x squared. And maybe I should use subscripts. Well, I'll just leave it like that. These are not the same x's, though. Why are these not the same x's? I'll go inner and outer. Inner and outer. Okay? And this is what we're trying to find. Because this spring up here, this outer spring, only gets compressed by 0.05 meters. The inner spring gets compressed 0.15 meters. So a lot more energy is going to be stored in that inner spring than in the outer spring. Okay, so what do we want? Well, we want 1/2 k naught x naught squared is equal to 3 joules minus this. And we know what this is. This is 1/2 of 200 newtons per meter. We already know that spring constant from part A. And then what is delta x? 0.15 meters squared. Okay. And what is that? I think this is turns out to, then when you calculate this, plug this in your calculator, you end up getting 0.75 joules. So in other words, there's 0.75 joules stored in that outer spring. And that's equal to 1/2 k naught x naught squared. And this will allow you now to solve for k naught. So k naught, or not k naught, k outer, right? The O stands for outer, the outer spring, is equal to 2 times 0.75 joules, right, divided by x outer squared. Well, what is x outer? How much did that outer spring get compressed? Look at the picture. 0.05 meters. So this is 0.05 meters squared. Figure out that, and when you do that, you get 600, and the units turn out to be, well, what's a joule? A joule is a Newton meter. This is a meter squared, so you get a meter, cancels the meter squared, you get newtons per meter, as we should. And that is, that's the whole problem right there. It stops at part E. So this problem is quite doable, as opposed to problem 1, which at least the last part of part 1 became ridiculous. So this is the kind of problem you really want to see, because you can nail this quickly if you know what you're doing and get all 15 points. So what are the big ideas that you should list here? Big ideas. Okay, area under a force versus displacement graph is what? Is work. I don't care how you abbreviate this stuff. You want to do it quickly. What else do we know? What's the slope? Slope of F versus X, if it's a spring, is the spring constant, K. Okay? What else did we use? We used the work energy theorem. The net work done results in a change in kinetic energy of our object. And then, of course, we had an exchange. We went from kinetic energy to elastic potential energy. That gives us conservation of mechanical energy. Now, make sure you know when this is true. When is E initial equal to E final? When the only forces doing work are springs and gravity. In this case, gravity didn't do any work. It was all springs doing work. So that means that you just have an exchange of mechanical energy from kinetic to elastic potential. Okay. So those are the big ideas I would list for this. So that is problem number 2 solved. Any questions?